Hi, my name's Adarsh Badala.
I'm Adrian Shex.
I'm Jack Lilly.
I'm Ian Falk.
And I'm Niels Haugen, and we are the Stellar Squad. Today is December 6th, 2023, and we're going to be talking to you about our AAE251 design project, the Stellar Space System.
Our mission stakeholders are taxpayers, citizens of the United States who would pay taxes that provide the funding for this mission, industry partners, companies who would be contracted to either manufacture or design specific portions of the system, and U.S. government and NASA, the primary overseer of both funding allocation and contract delegation for the mission program.
Moving on to our requirements, the stellar lander must have the capacity to retrieve a sample container containing all of the samples collected by the Perseverance rover. We have calculated the container to be approximately 0.0063 cubic meters. To successfully retrieve the samples, the total mission, delta V, must be at least 22 kilometers per second. Given that the calculated delta V required is 20.8 kilometers per second, an added buffer was implemented in case of emergency. Finally, given that the stellar system must be built and mission ready by the initial transfer window from Earth to Mars, the team has recycled prior art to save time in research and development, as well as the costs associated with them. With this strategy, the system will be ready for launch on our launch date of November 23rd, 2026. A number of potential risks our mission may encounter are the following, from highest to lowest risk. First is a launch vehicle failure. In order to mitigate this, we have selected a launch vehicle with a track record of reliable launches. Next risk is sample contamination. To mitigate this, we will ensure proper seals to make sure the samples come home intact. Third, biggest risk is cold welding. For this, we are designing our system with cold welding tolerances in mind. And finally, in case of asteroid collision, we will track objects in our path and plan our trajectory accordingly.
Our final system design included a kick stage, orbiter, and lander. The kick stage's purpose is to burn away from Earth, detach from the system, and initiate the Mars transit portion of the mission. The orbiter handles all burns in or near Mars orbit. The lander will be dropped into the Martian atmosphere, where the first stage will let the lander safely touch down on the Martian surface. The lander will collect the samples, then the second stage will launch back into orbit to rendezvous with the orbiter, where a sample containment unit will be transferred to the orbiter. After the lander detaches from the orbiter will burn to initiate the final leg of the journey back to Earth.
Now let's talk about delta V and mission design. We broke our mission down into 6 segments. The delta V requirements for each segment can be seen on the table here. We calculated the total delta V required for the mission to be 20.866 kilometers per second. Phase 1 of the mission involves the launch to LEO with the Atlas V launch vehicle. This involves taking off from Kennedy Space Center with an azimuth of 90 degrees. Then we're going to do a plane change to align us with the equator. When we're at a circular orbit of 332 kilometers around Earth, we're going to separate from the launch vehicle, and then our kick stage is going to initiate us onto a home and transfer to Mars. Then we're going to fly by Mars at an altitude of 100 kilometers. We're going to do a retrograde burn into a highly elliptical orbit around Mars with an apoapsis of 40,000 kilometers when we approach our closest point to Mars. Then, to save delta V, we're going to use aerobraking, which involves slightly entering the Martian atmosphere with each pass around the periapsis, which will thus decrease our speed and decrease our apoapsis until we reach a circular orbit around Mars. When we're at the circular orbit, the stellar orbiter is going to detach from the stellar lander, and then the orbiter is going to make a small burn to escape the Martian atmosphere, while the lander is going to continue on that same trajectory and continue aerobraking until it fully falls into the Martian atmosphere. Then, stage 1 of the lander is going to use a combination of a parachute and thrusters to safely land on Mars. When we're on Mars, the samples will be delivered to the sample containment unit by the Perseverance rover. Then, stage 2 of the lander is going to take off with the samples and rendezvous with the stellar orbiter around Mars. When they rendezvous in orbit, the lander will then separate, leaving only the sample containment unit and the stellar orbiter. The orbiter is then going to do a burn that will put us on a home and transfer back to Earth, similar to how we got to Mars. Except this time, the trajectory will take the sample containment unit on a path directly into the Earth's atmosphere, where it will then use a heat shield and parachute to land safely back on Earth, where we can recover the samples.
Now that we understand our mission profile, we're able to calculate the mass of our system, including the stellar orbiter, the stellar lander, and the sample containment unit. We did not calculate the mass of the kick stage as we wanted to calculate on the stages going around Mars. Our total mass was 5,605 kilograms with 4,278 kilograms worth of propellant. To calculate this, we used a MATLAB script that calculated each of the component masses of significance and summed them together. For example, for the stellar orbiter, we calculated the needed delta V for each operation, then found the needed propellant for each of the delta V changes, and then we found the tank mass needed to contain each of the propellants. After that, we found the engine masses and the structural masses needed to keep it all together. We did that for each of the stages and summed it together to find the total mass of the entire system. We also found masses for subcomponents like our heat shields and our landing legs based on reality, so real components that were tested and flown. For example, the Martian reentry heat shield that we used was based off of Perseverance's heat shield, and that gave us a more accurate value that translated to a more accurate total mass. Now that we understand our mass breakdown, we are one step closer to getting to Mars.
In order to calculate the timing for our mission, we used the relative motion of both Earth and Mars about the Sun to minimize the required delta V. By using a reference date for which Earth, Mars, and the Sun are linearly aligned, we used half the period of our elliptical transfer orbit to back calculate a date for which the end of our transfer orbit intersected with the motion of Mars around the Sun. This calculation resulted in an Earth departure burn, which will take place on November 23, 2026. After completing the mission, the Stellar Space System will wait in orbit around Mars until a similar transfer window opens up for the system to return to Earth. Doing the same type of calculation, but switching the constants for Earth and Mars, we found a Mars departure date of October 19, 2028.
This mission provided a comprehensive learning experience that touched upon skills related to both technical aerospace engineering design and group work. We learned about breaking down the mission into needs, requirements, and risks before approaching the actual design. We learned about optimizing delta V calculations and tailoring rocket stages towards our specific mission goals. Team-wise, the semester's journey taught us how to delegate work evenly and independent and group work balance.
That concludes our presentation on the Stellar Space System for Mars Sample Retrieval.
Thanks for watching. Hope you enjoyed.